All right, let's review gas laws. So the first thing that we need to know is how to convert from Celsius to Kelvin. And so our equation is Kelvin is equal to degrees Celsius plus 273. So when we have something in Celsius, we just add 273. Oops. And that will give us 302 Kelvin for the first one. Second one here, again, adding that 273 gives us 423 Kelvin. And lastly, adding 273 to negative 55 gives us 218 Kelvin. The next portion is doing pressure conversions. This is when we are going to be using our relationships between our units of pressure. So for every 1 atm, there is 760 millimeters of mercury and 101.3 kPa. And so this is what you'll see on the test. You need to make sure you know how to use these relationships. And so the first one here is we are going from atm to kPa. So the ones I'm focusing on are these. And so you guys should be pros at conversions now. We're starting with what we know. Well, if we have 3 atm, we're going to set up our unit conversion. If we want atmospheres to cancel, we're going to put atmospheres on the bottom, atm, and we are going to put our target units on top, kilopascals. The last thing you have to do is bring the numbers down with the units. So what you're going to end up having is for every 1 atm, there's 101.3 kPas. If you take 3 times 101.3, you get 300 kPa. So my mistake here is I accidentally had a typo. So really this 3.0 should be 3.00 atm. So I'm going to fix that here. The reason being is I want to make sure that my sig figs are held throughout the conversion. This answer gives us 3 sig figs. The next one here, we have 203 millimeters of mercury to atm. So, oops, what we are working with on this one is going between these two. And so starting with what we know we have 203 millimeters of mercury. Set up our conversion fraction here. And so millimeters of mercury goes on the bottom. And we want atm. Target unit goes on top of the fraction. And so filling in the numbers, atm gets a 1, millimeters of mercury gets 760. So if you take 203 times 1, divide it by 760, you get 0.267 atm. Again, following that rule of having 3 sig figs. Lastly, we are going to be looking from kilopascals to millimeters of mercury. That's going to be these two. And so starting with what we know, 234 kPa. Setting up our conversion fraction. We want to get rid of kPa, so we put that on the bottom. And we want millimeters of mercury, so we put that on top. Filling our numbers for every 760 millimeters of mercury, we have 101.3 kilopascals. And so for this one, you take 234 times 760, divide that by 101.3, and you get 1,760 millimeters of mercury. Again, 3 sig figs. Number 7 is talking about theory. So what did we learn about the kinetic theory of gases? And so what's important to note, there's kind of 3 main points. First of which is that we have the gas state particles move quickly. We also have that these gas state particles are far apart. And lastly, they don't bump into each other. So there are no interactions. They move independently. Now, the next 4 questions talk about the relationship between all the variables. And then number 12 is going to be showing those graphically. So we have, if you guys remember the PTV cards that we made. You can think about these as we're going through here. So if we are looking at the relationship between pressure and temperature, this is going to be direct. Pressure and volume is our only indirect relationship, and what I mean by that is when one goes up, the other goes down. So again, this is where if you took your pencil, put it through T, if you swung pressure down, volume would go up. This is our one indirect or inverse relationship. Volume and temperature, those are going to be direct. And then we also talked about Avogadro's law, which is pressure in moles. This is also a direct relationship. And another way to think about it is if you think about adding moles is like adding stuff in a container. As you add more stuff, you'd assume that the pressure would increase because it increases those collisions against the container wall, which is pressure. And so graphically representing these, if we have a direct relationship, it's just going to be a straight line coming from the 0, 0 point. So the only one that's not like this is the first one, pressure and volume. If you have an indirect relationship, the graph looks like this. That is also representing when we have an area. So think of this being low and high volume. This is low pressure and high pressure. What it's saying is at a low volume, we have a very high pressure. And at a low pressure, we have a high volume. And so this is the, if one goes up, one goes down, indirect type of relationship. Versus these other ones, these are all going to have the same type of graph. Where stuff towards the left side is going to be a low temp and a low pressure. But if you increase either, so does the other. So this is a high pressure, high temp. High temp, high volume, low temp, low volume. And then low number of moles, low pressure, high number of moles, high pressure. Moving on to number 13. So which of the following would half the volume of a contained gas at constant temp? So right now, we are looking, if you look in the answers, we're looking at the relationship between pressure and volume because we have constant temperature. We know this is our indirect relationship, meaning as one goes up, the other one goes down. In our case, we want to decrease volume, which means we're going to want to increase pressure. That's going to be doubling. Because remember when we did some mental math with the factors, if we had a volume that's initially at 1 liter, and let's say we want to make it to go to half a liter, this would be halving the volume, right? Well, this would be taking, it'd be multiplied by a factor of 1/2. With our inverse relationships, we are going to want to flip this factor and make it 2/1. So anything we'd be doing is doubling the pressure. 14. Which of the following would double the pressure of a contained gas at constant temp? Now, what we're looking at is pressure and number of moles. And what we know about this is our direct relationship. And so if we want to increase pressure, we better increase the number of moles. And so this is also going to be doubling. Because if you double one, you double the other. It's proportional. All right, number 15. A sample of gas has a volume of 2 liters at 101.3 kPa. If the temperature remains constant, what pressure would increase the volume? So again, we're going back to this idea of an indirect relationship. If we want to increase the volume, we better decrease the pressure. And the only option that has a lower pressure than the initial one is going to be B, which is the correct answer. So again, we're just looking for a lower pressure than the initial because of the indirect relationship. 16. What conditions of pressure and temperature give us the most ideal gas behavior? This is when we have low pressure and high temperature. Low pressure means that they aren't forced to interact with each other. High temperature gives them that energy for them to move quickly. So these are the most ideal conditions. All right, let's get into the calculations.